In 1969, the world caught its first glimpse of a technological marvel that looked more like science fiction than reality: Concorde. In an era when color television was still considered a luxury, this needle-nosed jet promised something extraordinary, cutting transatlantic travel times in half. London to New York in just 3 hours and 20 minutes. The juxtaposition was surreal. Passengers in the late 20th century flying at twice the speed of sound, while most households were still fiddling with black and white TV sets. Concorde wasn't just a plane, it was an anomaly in commercial aviation, a bold experiment in supersonic travel funded not by private airlines but by the British and French governments. Together, Britain's British Aircraft Corporation and France's Aerospace poured nearly $3 billion into its development. Though it ultimately failed to achieve commercial success, the Concorde remains one of history's greatest feats of engineering, a product of daring ambition, technical brilliance, and political pride. The challenge. Supersonic aircraft were nothing new in the 1960s. Military jets had broken the sound barrier years earlier, but those designs cared little for passenger comfort, noise, or cost. Adapting such technology for wealthy civilian travelers was a challenge unlike anything engineers had faced before. Military jets could rely on aerial refueling, tolerate ear-splitting noise, and burn fuel like there was no tomorrow. A commercial airliner had to satisfy very different demands: efficiency, safety, reliability, and, above all, luxury. Meeting these criteria required reimagining everything from engines to wings to passenger experience. Engines born from warplanes. At the heart of Concorde's design were its engines, the Rolls-Royce / Snecma Olympus 593 turbojets. Originally developed for the Avro Vulcan bomber, these engines evolved dramatically to power Concorde. The original Olympus units produced about 49 kilonewtons of thrust, but through continuous development they were pushed to 169 kilonewtons, over 3 times more powerful. About 20% of that extra punch came from the addition of afterburners, or reheat as British engineers preferred to call them. Afterburners worked like rocket boosters, injecting additional fuel into the hot exhaust gases to squeeze out more thrust. This came at the cost of fuel efficiency, but was vital for takeoff and acceleration to manage the complex flows and pressures created by afterburners. Concorde's engines used variable nozzles, systems far more advanced than those found on subsonic airliners. Concorde's nozzles and inlets. Ordinary airliners use fixed exhaust nozzles because they operate within narrow speed ranges. Concorde, however, had to handle everything from sluggish taxi speeds to Mach 2 cruise. Its solution? A dual nozzle system. The primary nozzle adjusted diameter to control pressure when afterburners kicked in, preventing choked flow that could disrupt engine performance. The secondary nozzle featured eyelid doors that acted as a converging-diverging nozzle, a design more common in rockets than planes. This setup optimized thrust at both subsonic and supersonic speeds, and even doubled as a reverse thruster during landing. Equally ingenious were Concorde's intakes. No jet engine can handle supersonic air directly. Shockwaves inside the compressor would spell disaster. To avoid this, Concorde's square inlets used movable ramps and doors to slow, compress, and smooth the airflow before it entered the engines. These adaptive systems were a masterpiece of aerodynamics, turning violent supersonic winds into orderly subsonic streams. Efficiency at Mach 2. Supersonic flight is notoriously fuel-hungry, yet Concorde's Olympus engines were remarkably efficient at cruise. The secret was the combination of intake compression and multi-stage compressors inside the engine itself. Together, they achieved a staggering pressure ratio of 80:1, far higher than even today's advanced airliners like the Boeing 787, which manages about 58:1. That efficiency came at a cost, though: extreme internal temperatures. To withstand the heat, Concorde used titanium and high-temperature nickel alloys in its compressor blades, materials normally reserved for the hottest turbine sections. This relentless pursuit of efficiency created countless engineering challenges, from bearing cooling to shaft stiffness. Every solution was unique, custom engineered for the singular demands of supersonic cruise. Wings of a different kind. While the engine stole headlines, Concorde's wings were just as groundbreaking. Unlike conventional airliners, Concorde used ogival delta wings, a compound delta shape with a smoothly curved leading edge. At high speeds, delta wings excel by minimizing drag, but at low speeds, they struggle to produce lift. Concorde overcame this with vortex lift. At high angles of attack, stable vortices formed above the wings, generating extra lift and keeping the aircraft airborne during takeoff and landing. This design demanded steep angles of attack during approach, creating serious visibility problems for pilots. The solution was one of Concorde's most iconic features, the droop nose. Style meets necessity. Concorde's sharp nose wasn't just for looks. During cruise, it stayed level with a heat-resistant visor covering the cockpit windows. But for takeoff and landing, hydraulics lowered the nose by up to 12.5 degrees, giving pilots a clear view of the runway. This clever mechanism balanced aerodynamic needs with operational practicality and became a signature part of Concorde's futuristic appearance. Paired with an extendable tail wheel to guard against strikes during steep approaches, it highlighted the aircraft's careful balance between performance and safety, heat, expansion, and material science. Flying at Mach 2 meant Concorde's skin endured temperatures of 130 degrees Celsius at the nose, while cruising through air as cold as minus 56 degrees Celsius. The result was dramatic. The aircraft lengthened by nearly 20 centimeters on every flight. To handle this, engineers turned to a special aluminum alloy known as hydrominium RR58, originally developed during World War II for jet engines. Stronger and more heat-resistant than conventional aluminum, it became the backbone of Concorde's fuselage and wings. But the expansion couldn't simply be ignored. Panels slid past each other, wiring had built-in slack, and corrugated components acted like springs to absorb stress. Pilots even witnessed expansion firsthand, as a gap would open between the flight engineer's console and the cockpit bulkhead during cruise. Fuel as a balancing act. Fuel wasn't just energy for Concorde, it was also a control mechanism. The aircraft had 13 tanks holding up to 119,000 liters, cleverly distributed throughout its slender fuselage and delta wings. As the plane accelerated, its aerodynamic center of pressure shifted backward. Instead of relying on large control surfaces, which would have added drag, Concorde engineers used fuel transfer. By pumping up to 20 tons of fuel rearward during acceleration, they kept the aircraft balanced without compromising performance. It was an elegant solution, marrying aerodynamics with fluid dynamics. Maintenance nightmares. The brilliance of Concorde's design also created extraordinary maintenance demands. Sealants inside the fuel tanks, for example, had to remain flexible despite constant heating and cooling cycles. Even advanced materials like Viton hardened and cracked over time, forcing major maintenance every 1,100 flight hours. Technicians would spend weeks inspecting and resealing tanks, sometimes working entirely by feel inside narrow wing cavities. The costs were astronomical, one of the many reasons Concorde never became financially viable despite its engineering brilliance. The legacy of Concorde. Concorde carried passengers from 1976 until 2003, when a combination of high operating costs, low ticket demand, and the tragic crash of Air France Flight 4590 sealed its fate. Today, grounded Concordes serve as monuments to both ambition and limitation. One such aircraft, Alpha Bravo, still rests at Heathrow Airport, caught mid-refurbishment when the fleet was retired. It remains a silent reminder of what once was, a time when the future of air travel seemed supersonic. Why Concorde still matters. Concorde's story is more than nostalgia for a glamorous past. It's a testament to the limits of technology, economics, and human ambition. It proved that supersonic travel was possible, safe, and breathtakingly fast. But it also highlighted that speed alone couldn't overcome noise restrictions, fuel costs, and market realities. Yet the innovations Concorde introduced, variable inlets, advanced alloys, droop noses, vortex lift, continue to influence aerospace engineering today. And with new companies exploring boomless supersonic jets, the dream may yet return, building on the foundation Concorde laid half a century ago. And that's the story of Concorde, the supersonic dream that soared ahead of its time. If you enjoyed this deep dive into one of aviation's greatest engineering feats, don't forget to hit that and make sure to subscribe. Thanks for watching, and as always, keep looking up because the next great leap in aviation might be just around the corner.